My name is Robert Saint. I'm the Dean of the Faculty of Science here at the University of Melbourne, and it gives me great pleasure to welcome you all here this evening. Before introducing Professor Dennett, I'd like to acknowledge the Wurundjeri people as traditional owners of this land and pay respects to their elders, both past and present, and the elders of the Kulin Nations, I should say. Daniel Dennett is University Professor and Austin B. Fletcher Professor of Philosophy and co-director of the Centre for Cognitive Studies at Tufts University. Professor Dennett received his Bachelor of Arts in Philosophy from Harvard. He then completed his PhD at Oxford in the remarkably speedy time of 2 years. After 5 years at the University of California, Irvine, he moved to Tufts University, where he has taught ever since, aside from periods visiting at Harvard, Pittsburgh, Oxford, the École Normale Supérieure in Paris, the London School of Economics, and the American University of Beirut. Professor Dennett is one of today's most distinguished philosophers, as I know that many of you will know. Over the past 40 years, he has had a major influence on our understanding of human intentionality and agency, consciousness, developmental psychology, cognitive ethology, artificial intelligence, and the one close to my heart, evolutionary theory. He's author of a number of best-selling books that I can tell him at first hand were very influential to me as a young person dabbling in science, and has published over 300 articles on various aspects of the mind in a broad range of academic journals. Professor Dennett is in Melbourne to speak at Creative Innovation 2011, but tonight it's a great privilege to have him to address us this evening. Professor Dennett.
Thank you very much, Dean, and thank you all for coming out. This is a wonderful audience. I'm thrilled to be back in Melbourne. And so tonight I'm going to talk about the evolution of purposes. And I'm going to give you a little outline of what I'm going to do. First, I'm going to look at two species of why questions, two different species and a few subspecies. These are the what for sense and the how come. Then I'm going to, this is interesting. I find that I really have to get a little closer to my laptop, see what I'm saying. Darwin's contribution to this issue is the evolution from how come to what for. Then I'm going to talk about how we human beings, are the only reason representers in all of nature. And then I'm going to talk a bit about the intentional stance in both the manifest image and the scientific image. There's three jargon terms right there, but by the time I get to them, you'll understand what I'm talking about, if you don't already know what they are. So, okay, first, two species of why questions, what for and how come. So why is actually ambiguous in English. There are actually more than two senses. Why does ice float? That's a pretty good why question. But that is, I think, primarily a how come question. That is, what we want is an answer from physics to tell us how come it is that ice floats. But why are you handing me your camera? Is clearly a what for question. It's asking a reason, some goal that you have in mind when you're doing this. Now, some questions are apparently ambiguous. It's not clear which of two senses, or maybe both senses. I'll give you an example. Why do pigeons bob their heads? There could be both kinds of answers to that question, and that's really what I'm going to be looking at, is the transition from one to the other. This is the topic of teleology, which since Aristotle has been a vexed topic both for philosophers and for scientists. Aristotle was the philosopher-scientist. He was certainly as good a scientist as there was in his day and for many centuries thereafter. And he distinguished four, this is often translated causes, four aitia. These are four questions that you ask about something. What's it made of? The material cause. What's its shape, in effect, what are its formal properties, its formal cause, then the efficient cause is what triggered it, what caused it. That's more or less our everyday sense of cause in most contexts today. And then his fourth cause is the one that causes all the problems, and that's the telic, or final cause. And this is where we get the word telos, is the Greek, and this is where we get the word teleology, the idea of a why question being answered, where what you're asking for is what the French would call a raison d'etre, a reason for being. And ever since Aristotle put this forward, we've had controversy, anxiety, confusion about just what to make of final causes, or teleology. And then in the middle of the 19th century, Darwin came along with the theory of natural selection, and a lot of people thought, good, now we've got an account of teleology. Marx, for instance, said this: not only is a death blow dealt here for the first time to teleology in the natural sciences, but their rational meaning is empirically explained. Now, let me just go back. He seems to think that Darwin dealt a death blow to the notion of teleology. But then he goes right on to say that Darwin is explaining the rational meaning of teleological claims. Well, can you have it both ways? If there is a rational meaning to them, and if Darwin explains it, then it's not such a death blow after all. It's a founding of the idea of teleology. Which is it? That's really the question that I want to explore. It's one that philosophers and scientists have spent a great deal of time in over the years. So did Darwin find a safe place for teleology in science? Or did he show that, strictly speaking, there's no teleology, there's no purpose in the material world at all? What amazes me, actually, is today, at this point, there are actually quite a few scientists and a few philosophers who think the second is the truth, and who are so afraid of teleology. They have been taught so ferociously over their years, since they were undergraduates, thou shalt not sully science with teleology. This is bad, old-fashioned Aristotelian stuff, that they don't want any part of teleology at all. Whereas what I'm going to be arguing is, no, it's really the other way. Darwin is the friend of teleology. Darwin shows how to make honest science of teleology. That is sort of the punchline of what I'm going to be talking about. Now, often we hear about reduction, too, and we can ask the question, does natural selection reduce telic causes to efficient and formal causes? That's what a lot of people would want to say. But sometimes when they say this, they mean this in the sense of that gets rid of telic causes altogether. It turns out that telic causes are just something that we can handle quite well just in terms of efficient and formal causes, or efficient material and formal causes. But there's another sense in which one might think, well, if we had a nice reduction of final causes to these others, then we would have a theory of final causes. Isn't that the point? Isn't that what we want? Well, let's see where we get. It's a cartoon that I like. It really does size up the difference between a human mind and an animal mind. And what I want to point out, of course, is that why makes its appearance there. And why me, but why? And that is, I think, the most important question that this fellow is asking himself. And one of the things I want to claim is we are the only species that asks why, or even thinks why. We're the ones who make the question, the issue of why, an issue. Well, now let's look at the different senses of why. There's the what for sense. Philosophers recently have made a lot of this at the University of Pittsburgh. I somewhat snidely, I guess, call this Pittsburgh normativity, because there's some eminent philosophers in Pittsburgh, Robert Brandom, John Hoagland, John McDowell, formerly of Oxford, who, for whom the idea of normativity is very important, and it's all about why. Brandom, following his hero and mine, Wilfrid Sellars, likes to talk about the space of reasons. Well, the space of reasons is the space, the logical space, where we debate about reasons, where we, when somebody comes up and says, why are you doing that? You say, well, this is why I'm doing it. And they, well, why are you doing that? Well, in order to do this. Well, why are you doing that? This cascade of reasons and challenges and further justifications, that's the space of reasons. Kids learn this at a young age. Daddy, why are you sawing that plank? I'm making a door. Why are you making a door? So we can close the house. Why do you want to close the house? Shut up. You know, something like that. The thing is, the kid will go on forever. You know. So it's the practice of asking and giving reasons and evaluating them. So it's a matter of justifying oneself or somebody else, or asking for justification. So that's Pittsburgh normativity. That's what for in a very strong and rich and even moral sense. How come, on the other hand, is asking for a process narrative with no suggestion or presumption of justification. Why does ice float? Now, after I used this example, I thought, well, you know, there's going to be some people who want to treat this as a teleological question. And they think, well, you see, God wanted ice to float so that, you know, the fish could live in the winter in the lake, so that man could have fish all year, or something like that. But we don't have to treat the question that way. We don't have to look for God's reasons. We can just ask for the physical account. What is it about ice? What process, when ice freezes, when water freezes, what is the process that makes the resulting solid of lower density than the water in which it is floating? So it can be seen as a pure how-come question. Now, the difference between the how-come sense of why, which asks for a process narrative and no justification, and the what-for sense, which is asking for a justification, it's obvious enough, I hope, but I want to make it super vivid by giving you an example to tie it to an anecdote from my past. B.F. Skinner, the great behaviorist, was famously a critic and opponent of teleology. And I was once engaged in a debate at Western Michigan University back in 1974. I looked up the date. Now, Western Michigan University was to Skinnerian behaviorism roughly what the Vatican is to Roman Catholicism. It was card-carrying Skinnerians filled the psych department there. And I was called out there to do a debate with the chairman of the department, in fact, a man named Lou Michaels. And we had a debate in a room which was maybe twice as big as this one, and packed to the rafters. This was a very ardent issue, strangely enough, at Western Michigan at the time, and it went on for hours. But at one point, and Lou Michaels was a wonderful, honest and constructive debater, and at one point in the discussion, late in the evening, he had just delivered himself of a particularly ripe bit of Skinnerian dogma. And I said, but why, Lou, do you say that? And his instant reply was, because I've been reinforced for saying that over many years. True to his calling, true to the Skinnerian vision. But notice he didn't answer my question. He gave the process narrative and didn't even try to do the justification. Right there you can see the gap between the two questions. And you can also see why so many people at Western Michigan University were deeply afraid of and distrustful of the behaviorists, because they wanted to replace all those good why questions, all the good what for questions with process narratives and just leave out justification altogether. Okay. There are, as I've said, two species of subspecies of what for. There's Pittsburgh normativity, and then what we might call consumer reports normativity, where what we're interested in is just the quality of an item, not whether it's morally good, just whether it's a good buy, whether it's good value. And in order to have normativity at all, you have to have corrections. You have to have some process or something dynamic that tends to identify and at least attempt to correct the errors, the falling short, or enforcement. Now, for Pittsburgh normativity, this is social correction, nicely brought out when John Hoagland speaks of censoriousness and a certain censoriousness in society which, naughty, naughty, mustn't do that, which he views as one of the prime movers of founding and giving impetus to the space of reasons. For consumer reports type of normativity, it's the norms of good design that are at issue of good value. And now the question is, well, what process corrects to those norms? It's obvious. Market forces, quality control, or in the case of biological entities, evolution. These are processes which have the effect of making things better, improving the design of things, whether they're artifacts or organisms. So evolution engages in a kind of consumer reports correction. And the difference between these two senses of why, what for, the Pittsburgh and the evolutionary sense, can be brought out in another sort of vivid way. It's the difference between naughty, that's the Pittsburgh term, and stupid. One of them has a moral overtone to it, and the other one is just saying, dumb design, pay for it with your life. What evolution says. Okay. Okay, we've already been through this. I got some slides out of order here. So the justification that Pittsburgh normativity, that both kinds of normativity ask for is, in one case, why is this thing good? And it is either like a good deed or just like a good tool or a good hammer, which is the evolutionary question. Now we come to process narratives. How come? As I said before, it does not imply or presuppose any sort of justification. I want to make sure you understand it by giving you some examples. In failure analysis, why did this turbine blade snap? You certainly don't want a justification. You want a process that explains this flaw. Why did that building collapse? Or historical explanations usually fall in this camp. A particularly vivid and interesting example is Ian Morris's recent book, Why the West Rules for Now, which is certainly not the what for sense of why, it's the process narrative, and a very interesting process narrative it is. So when do we use how come? Well, for natural saliencies, why is the sky blue? Or why is the sand on the beach sorted by size? Not that it should be sorted by size, because that's the way it ought to be. It's naughty if it isn't, or stupid, but just what's the process narrative that explains this? These are some photos of Boom Beach on an island in Maine near me, where we go in the summer, where there's just thousands and thousands of cannonball-sized rocks, which are egg-shaped or round. Some of them are almost perfect cannonballs. And you come up to this incredible pile of cannonballs, and you just, why are they here? How did they get here? This clearly is asking a how come question. But if you found those in some contexts, you probably ask the what for question. There are cases of things where we're strongly tempted to replace the how or supplement the how come question with the what for. For instance, the Cappadocia fairy chimneys seem to speak out as if these are some sort of artifice made by an agent with some kind of intention. But in fact, no, they're just dumb natural effects of the weather on the tufa, on the volcanic stone in the area, and how they come to have those amazing shapes is itself an interesting story. And sometimes we'll see some things where it's hard to say. Now here are two rather similar phenomena. One of them, the one on the left, is actually a work of art. It's an Andy Goldsworthy, and he does amazing, wonderful sort of sculptures out of natural materials, and this is just one of many that he's done, gathering rocks of different sizes and shapes and then arranging them in striking ways. The one on the right, you might, if you came upon it, you might think, oh, look, Andy Goldsworthy has been here making these. But in fact, no. This was the cover of Science a few years ago, and this is a process that is made without any intervention by any artist or any human hand or intention at all. It is a result of cycles of thawing and freezing in the Arctic. So, now we come to what is really the heart of my talk, which is Darwin's contribution. That is, how do we get from how come to what for? So here's my hero, Darwin. Very gradual change you can believe in. And the gradualism is very important. What I've been claiming for some time now is that natural selection should be seen somewhat anachronistically as an algorithmic process. That what Darwin actually discovered, he didn't have the vocabulary for it, is that natural selection is a set of algorithms which perform certain operations very efficiently. They're sorting algorithms, of course, not unlike the algorithm that sorts the sand on the beach. Not designed by anybody, it's just a process that mindlessly does this work. Moreover, they're what in artificial intelligence would be called generate and test algorithms, where you blindly and stupidly generate a whole bunch of candidates and then you test them, throwing out the ones that don't fit. So natural selection fits very nicely into the species of generate and test algorithms. And like many other algorithms, makes heavy use of randomness along the way, just to generate the diversity, just to get you off the dime so you have a bunch of candidates. As I say to my students, don't worry, write something that's wrong, then you have something to fix. And don't think you have to get it right from the beginning. Now here's a question that is not yet answered. How does evolution by natural selection get started? The problem of the origin of life is a very interesting theoretical problem. It's one that fascinates me, and it is unsolved, although I would say there's an embarrassment of riches. We have too many ideas that haven't been disproven yet, so we're not desperate by any measure, but we don't have a good answer to this question yet. But I want to give you some ideas. This is, I think, some of the keys to how it's going to be solved. I want you to think about cycles in abiotic or prebiotic nature. That is, before there's any reproduction at all, when there's just geology and physics and chemistry. In the abiotic or prebiotic world, do we have cycles? And the answer is, yeah, we have lots of them at many different scales. We have the seasons. That's a cyclical, long-term process. We have night and day. We have the tides. We have the water cycle. And then we have thousands and thousands of chemical cycles at many different scales. I want you to consider cycles as do loops, what a programmer would call do loops, which keep doing something, do it until, and then do something else. Do loops are ubiquitous, of course, in computer programs. And I want you to think of abiotic cycles as natural do loops. What's interesting about a cycle is that it returns again and again to the starting point after accomplishing something. Well, sometimes it doesn't seem to accomplish anything. Sometimes it seems to be just completely idle, round and round it goes, futile cycles. But in fact, sometimes, imperceptibly, there's a little change. And I think this is one of the great discoveries, actually, of human beings, is that you can have a process which seems not to change at all, but imperceptibly, over time, it accumulates change. Let me give you an example. The first human being who took a stick and a stone and rubbed the stick on the stone all day long, turning it slightly, probably looked like a complete idiot. And if you looked at the stick from moment to moment, you wouldn't see any change. But at the end of the day, he had this beautiful straight arrow. He gradually wore it down, had the patience to see that if you just kept going, you could actually create something quite remarkable and even unnatural in a certain way. That's a cycle. Cycles can accumulate things, or move things, or remove things by a process of gradual repetition. Or they can sort things. And any of these processes then change the conditions in the world, and here comes the important part, raising the probabilities that something new will happen. I love it when somebody will listen to one of the accounts of how maybe life got started on the planet. We'll hear some process like this described, and the person will say, you know, that wouldn't happen once in 1,000,000 years. You say, okay, how about once in 10 million years? We got a lot of time to work with. It only has to happen once in 10 million years. If it can happen once in 10 million years, you know, we're golden. We're going to have a good solution. But you have to have cycles to raise the probability over time, so that if you keep doing it, it becomes the conditions. You sort through conditions again and again and again, and you just have to get to the right conditions once, and then something new happens, and then it starts a whole new process. This is a nice example, this one from science, a self-organization of sorted patterned ground. I don't know these fellows at all, but I love their article, and they have some wonderful, these are from that science article. These are species, that's their term, species of sorted ground, and they have some nice diagrams that explain the feedback processes that occur during this freezing and melting cycles and how they tend to aggregate the stones. And they even wrote a simulation, a little computer program which runs the process again and again and again, and you can set it up and watch it run and see how it gradually forms various patterns, all without any deliberate hand being introduced. So here's what I think happened in the early abiotic, prebiotic days on the planet. We had gradually growing algorithmicity. That is, there were processes, there were cyclical processes, and they kept changing the conditions on the planet and changing the conditions and changing the conditions. And don't look at your watches, it's going to be millions of years of changing conditions. But every now and then a change set off a new process. And so it continued. And of course, I'm speaking in philosophical generalities, but the people who work in this field have lots of ideas about exactly which processes are the important ones. initially you have what looks like parallel processing, many instances of the process happening at once, all over the planet, or wherever there's warm ponds, or wherever there's hydrothermic vents, or wherever there's ice. And in all of these places, you have these processes just happening over and over and over again. And so you have a certain sort of mass production in this parallel processing. And what happens is that mass production turns gradually, gradual change you can believe in, turns gradually into mass reproduction. Well, how? That's easily said, but not so easily shown. I want to suggest that there's actually a gradual transition from differential persistence to differential reproduction. Long before there was reproduction, before there were genes, before there were offspring, there was differential persistence of processes and phenomena. Some things hung around longer than other things. And whenever something hangs around longer than something else, that gives it just more opportunities to accumulate change. How? Oh, anything. By picking up a piece of junk, or by getting a scar, or being misshapen in some ways. And then who knows what could happen next. Two terms from computer programming, clobbering and serendipity, often used. Clobbering is when you've got these two processes, and individually they look just great and they work very well, but if you put them together wrong, one clobbers the other and simply prevents it. And software engineers go crazy trying to prevent clobbering in their large software projects. But of course, nature's way, since there aren't any intelligent designers involved at all, doesn't give a hoot about clobbering, and clobbers all the time, a lot of clobbering. And as a result of being tolerant of clobbering, this gives room for serendipity. Things that, as it were, human engineers and creative designers, intelligent designers, would try to isolate, keep apart, because they're worried about clobbering, can be allowed to come together, and then sometimes you get these wonderful serendipitous effects which improve things. Think about a membrane as a clobbering preventer. This seems to be essential for the origin of life, for creating the first reproducing form, because it has to have do loops inside it that operate without interference. So you have to have a wall between the do loops that are doing the good work, but I'm not talking, there's no good yet. It's all just process. But we have all of these cycles, Krebs cycles, thousands of other cycles. These are now understood as just the foundations of biological processes at every scale. And you can even think of biochemical cycles. They're in effect the nervous systems of single cells. So even though a single cell, like a bacterium, doesn't have a nervous system, it's just one cell, but it has a sort of molecular nervous system which consists of these algorithmic cycles going on in the chemistry. A book which I highly recommend is Dennis Bray's book, Wetware. Came out a couple of years ago. It's a virtuoso account of computing, subcellular computing, and using mainly protein networks. Persistence, as I was saying, give things extra time to pick up revisions and adjustments. And I want to suggest that reproduction is just a special kind of persistence. A very special kind, but that's what it is. It's the creation, instead of just hanging around, of making copies so that you have tokens of types. And what persists even better then is the type, because it has many tokens. And those tokens can then go out and explore the corners of the world in parallel, and they can actually carve up space and look at different areas for further enlightenment. So the familiar maxim, don't put all your eggs in one basket, is you might think the first axiom of population thinking. And once you've got reproduction, then the fact that you've got all of these independent or semi-independent tokens of types to do the exploring gives you a sort of robustness, a certain sort of persistence or likelihood of persistence that is otherwise lacking. My friend Rod Brooks had a famous theory about robotics, which got the wonderful sort of bumper sticker slogan, fast, cheap, and out of control, which then some of you may have seen the movie that Desmond Morris made called Fast, Cheap, and Out of Control, about that work and others. Errol Morris movie, not Desmond Morris. So now we're ready, from how come to what for. As these cyclical processes continue, the focus shifts gradually. Some features are becoming ubiquitous. We can ask, why? Why are we seeing these features, these patterns in the world that we didn't used to see? And the question now is equivocal. We're asking for a process narrative, but we're also asking in a way for a justification. Because these are things that are good at persisting. The reason we're seeing them is because they're better persisters than the competition is. Now, this is Darwinism about Darwinism. It's very important. Remember, gradualism is a key. And what I'm actually saying is the transition from how come to what for is itself gradual. And you go through a period where the questions are ambiguous, or you can ask both questions at the same time. And so you gradually establish a base to ask the what for question, which grows out of the prior understanding of how come questions. So why questions themselves can be seen to evolve during this period. So it's from narrative to justification. Physically possible, chemically possible alternatives at some point are absent. Why don't we see any more of that here? What we're seeing are things that are better at persisting and reproducing in the local circumstances than the alternatives. We are witnessing an automatic paring away of the non-functional. This is Tibor Ganti's elegant sort of engineering description of the chematon. What do you call the chematon? This is the simplest requirements for life. And you'll see that he's got a membrane, a genetic system, and a metabolic system. You need all three. All three of these, there are cycles that control all these. There's the membrane forming system and maintaining system. There's the genetic system, and then here's the semi-permeable membrane with waste, nutrients coming in and waste going out. And there's pretty much agreement, I think, among cell biologists that these are the basic components of a living thing. By the time you get to this, you've got function galore. You can say, this is the system that's here for taking care of the reproduction. This membrane here is for clobbering prevention, for keeping the thing together, for keeping the outside world at bay, and also for providing a gateway for the stuff that you have to take in. Oh, wrong button. And so we get the birth of reasons. By the time we get to a reproducing bacterium, there's functional virtuosity galore. In other words, there are reasons why the parts are shaped and ordered as they are. Perfectly good reasons. We can ask and answer the why questions and get what for answers. We can reverse engineer any reproducing entity, determining what's good for it, what's bad for it. and why it's good or bad. So what I'm suggesting is that natural selection is an automatic reason finder, which discovers, endorses, and focuses reasons over many generations. Notice I put all those terms in scare quotes. It sort of discovers them, it sort of endorses them, because of course natural selection is not itself an agent. It's not an intelligent agent. We might call it Mother Nature just because it's fun to talk that way. But don't be misled. We're not saying that natural selection has purposes and goals or that represents these reasons. It doesn't represent the reasons, it just finds them. I want to cash out those scare quotes to try to convince you there's no cards up my sleeve here. Consider a population with lots of variation in it. Some do well, some don't. In each case, we can ask why. And in many cases, the answer is going to be no reason, just luck, good or bad. So let's suppose most of the time when we ask the why question, there's no reason at all. Every now and then, however, if there's a subset, very small, of cases where there is an answer, this one did better because it had this feature which protected it, which aided it, which enhanced its capacity, and so forth. Fitness, in other words. A difference that made a difference. Then we have the birth of a reason. What the cases have in common provides the germ of a reason. And then natural selection enhances and polishes and optimizes that and establishes a new design feature which has a reason and which by its very existence brings a standard, a normative standard of value. There's good membranes and not so good membranes, and better membranes and membranes that aren't worth a darn. We are introducing normativity into this otherwise bland process talk. So natural selection tracks reasons, thereby creating things that have purposes, but that don't need to know them. Bacteria don't have to know what the purposes of their parts are. I've often talked about the need to know principle, made famous in spy books and movies, where the rationale for the need to know rule is keep your agents as ignorant as possible, so that if they ever get caught and waterboarded, they spill their guts, they don't have much to spill. The security is the rationale, the raison d'etre of need to know in spycraft. But in nature, it was a very simple rationale. It's just economy. Don't bother giving organisms expensive gear if they don't need it. And in fact, most organisms do not need to have any understanding at all of the things that make them good. They can be the beneficiaries of all their good design without having any clue as to why this is good design or how it's good design. They will still be the beneficiaries of it. And natural selection itself doesn't need to know what it's doing. Now, this is, I think, the great Darwinian insight, that a process, natural selection, can make magnificent, wonderful designs, and it doesn't need to understand what it's doing at all. It doesn't need to know what it's doing, and it can uncover reasons of breathtaking ingenuity without ever representing them at all. Which is just what Robert Beverly Mackenzie, my favorite critic of Darwin, said in a passage I love to recount. In the theory with which we have to deal, absolute ignorance is the artificer, so that we may enunciate as the fundamental principle of the whole system that in order to make a perfect and beautiful machine, it's not requisite to know how to make it. This proposition will be found on careful examination to express in condensed form the essential purport of the theory, and to express in a few words all Mr. Darwin's meaning, who, by a strange inversion of reasoning, seems to think absolute ignorance fully qualified to take the place of absolute wisdom in all the achievements of creative skill. Exactly. That's it. Bingo, you got it. That's it. And it is a strange inversion of reasoning. It's so strange that a lot of my countrymen still can't accept it. It really does turn things upside down. It gets rid of the whole idea of an intelligent creator that understands. My other main hero is Alan Turing. 2 years ago, I was running around the globe talking about Darwin for Darwin Year in 2009, and next year I'll be running around the globe talking about Turing, because it's going to be the centennial of his birth. And he had his own strange inversion of reasoning, and in fact, it was a version of Darwin's. Here's a photograph of some pre-Turing computers. They're wearing dresses. Computer was a job. That was a job description. What are you? I'm a computer. That's how I earn my living. And at the time, it was considered a fairly technical job. You had to be good at arithmetic, of course. You had to have some understanding of what you were doing. In the old days, computers had to understand arithmetic, and they had to appreciate the reasons. And Turing, his great insight, very much like Darwin's, was he recognized this was not necessary. That he could make a machine that didn't have a trace of understanding, absolute ignorance, that could do perfect arithmetic and conditional branching. And that's all you needed to be able to do all this wonderful computing. So I want to highlight this by putting the two. This is Mackenzie talking about Darwin, and he put it in capital letters when he wrote it too. He was in high dudgeon when he wrote this. But here's the Turing version. In order to be a perfect and beautiful computing machine, it is not requisite to know what arithmetic is. What they both, in their different ways, jointly discovered, and it is a strange inversion of reasoning, is, here's my bumper sticker, competence without comprehension. And notice how much of a violation of received wisdom this really is. Talk about a strange inversion of reasoning. Why are you at the university? Because people have been telling you since you were a little child, we want you to understand so that you will be competent. Comprehension is the source of your competence. We don't want you just to learn by rote. We want you to understand, because that makes greater competence. And of course, for us, and in many regards, that's true. And we've all learned that lesson, that in order to be really competent, you want to understand what you're doing. And it's that actually very sound educational philosophy which Darwin and Turing, in their different ways, simply invert. They say, well, yeah, in some cases, that's true. But as far as designing the biosphere or computing, doesn't follow. You can have absolute ignorant processes that don't understand anything that accomplish all these marvels, just exactly as Mackenzie said. And this has the effect of putting understanding, mind, consciousness, intention, all the things I've been working on my whole career, not as the original cause, but as an effect, and a fairly recent one at that. I think the way to understand this is you have to get used to a very Darwinian locution. In fact, you have to get used to what I call the sorta operator. The CPU sort of understands add and subtract. The operating system sort of understands where to file away the work in progress when you switch tasks. The search engine sort of knows the difference between salt and the salt treaty. The airline reservation system sort of understands when you say you want to fly to Chicago, and so forth. Before Turing, people said, oh my gosh, you have to have people that really understand those things before they can do any of that. No, we now understand. No, sort of understanding does just fine. There's lots of things that you can do with sort of understanding. Sort of understanding is a great building block out of which to build real understanding. So that comprehension, in the strongest sense, can be composed of competences which are only sort of comprehending. Deep Blue sort of understands the changing value of a knight as the chess game progresses, and so forth. Okay, we've done the first two, now we're coming to three. We're the only reason representers. This is the caddis larva food sieve built by this larva in freshwater streams to catch food. And you can see how the water goes in here, and the caddis larva has constructed this sieve, this net in the middle of this chamber, and the water passes through here and the food all gets stuck here. Oh, and there's also this, you can see in the top view, there's this protected chamber, a little tunnel, so it can go both sides of its sieve without going outside. Brilliant piece of design. Brilliant piece of design. Great way of sieving food from the water. Here's another device for sieving food from the water, a lobster trap. They actually have some principles in common, sort of interesting to do the engineering for both of them. Now, what's the difference between them? There are reasons for the arrangement of the parts in the lobster trap. Ask the lobstermen, ask the people who made and designed the lobster. They'll tell you the reasons. But there's also reasons in the case of the caddis larva's food sieve. There's reasons why the parts are the way they are there too. The difference is that the caddis reasons are not represented anywhere, not in the caddis larva's tiny nervous system, and not anywhere at all until some clever biologist comes along and reverse engineers the thing and figures out the reasons. When some biologist comes along and explains why this is good design, that's the first time in the history of the planet that the reasons have been represented. But they're the reasons all the same. Two very similar artifacts made by animals. The one on the left is a termite castle. The one on the right is Gaudi's La Sagrada Familia. They could not be more different in the way they were designed and constructed, even though they are deeply similar in shape and also in many structural details. The difference is that the termite hill is built by an entirely bottom-up process. There's no blueprints, there's no understanding, there's no boss, there's no architect, there's no king, there's nobody ordering anybody around. It's just a whole lot of termites just mindlessly doing their little local myopic thing, and this amazing structure emerges from it. Completely the opposite is true in the case of Gaudi. There was an intelligent creator, if ever there was one. I mean, this was the archetypal mad genius. He has the blueprints, he's got the rationale, he's got it all worked out. He can tell you why every piece is the way it's going to be, and he's ordering people who are ordering people who are ordering people around, top-down building with a vengeance. The results are quite similar, but two very different processes, natural processes, are building these. Now, with those two examples, we can take a deep breath and ask some questions. I say there's a reason why the termite does what it does. Not that the termite has a reason. There is a reason why the termite does what it does, but the termite, stupid little thing, it doesn't have that reason. It's not clued into that reason. Gaudi, on the other hand, has the reasons why he's doing what he's doing. He may be wrong, but he's got reasons. He's worked it out. He's represented those reasons. Human beings have reasons. Now here's an interesting question. Do animals have reasons? Other animals. They do things for reasons, but do they have them? It's not the same thing as having a reason for doing those things. This is what I call free-floating rationales. Trees do things for reasons. They don't even have nervous systems. But they do things for reasons. We can certainly talk about why they behave the way they do. Fungi do things for reasons. Bacteria do things for reasons. None of them represent the reasons at all. But that's the reason they're doing them. The biotic world is saturated with reasons from the molecular scale on up. And we do things for reasons that we don't have. We shiver, we vomit, we blink for reasons. There's reasons why we do those things, but we don't have to understand those. We're the beneficiaries of those phenomena. We don't have to understand why we're doing them, we just do them. One of my favorite examples of this is the cuckoo chick. Cuckoos, as you know, are brood parasites. The cuckoo doesn't make her own nest. When she's ready to lay her egg, she finds a host species, some wrens or some other birds, and she waits until those birds have laid, well, the mother has laid the eggs in that nest, and then when the parents go off to feed, the cuckoo sweeps down, deposits, lays her egg, her cuckoo egg, in that nest, and then, typically, not always, rolls one of the eggs out. Why? Why? What for? That's in case the host species can count. The cuckoo chick, it is. But the cuckoo doesn't have to understand that. When the cuckoo chick hatches, and it hatches before the other eggs, and there's a reason for that, the first thing it does is it wrestles and wrestles and pushes, devotes all of its energy to pushing the other eggs out of the nest so that it can monopolize the food of its foster parents. But the little cuckoo doesn't have to understand this. It knows not what it does. It's engaging in ovicide, but it doesn't have to understand the rationale of this at all. But we can understand the rationale. The rationale is perfectly clear. There's a reason why the cuckoo rolls an egg out when she lays her own. There's a reason why the cuckoo chick pushes out the eggs when it hatches, as there is a reason why trees spread their branches. But they don't have to be appreciated by the beneficiaries, who do not have to be reason representatives. We are the only reason representatives. Think of us when we were children. You can speak well without even knowing why or how it works. Becoming a sort of self-conscious theorizer about your own utterances and your speech acts is a very sophisticated thing. But you can be a very good conversationalist without ever having figured that out. I'm going to pass over that. Now this raises a very interesting question. Is an ape more like a termite colony or like Gaudi? The termite colony does all sorts of things for reasons, but doesn't represent any of them. Do apes represent their reasons? Or do they just do things for reasons? As usual with evolution, there's intermediate cases. My friend Ruth Millikan, wonderful philosopher, talks about animals that represent their goals in the same representational system in which they represent their facts. And this is one of the nice evolutionary steps, a gradual step towards being like us and representing reasons. Another friend of mine, Nick Humphrey, has often called apes natural psychologists. They're very good at sort of reading the minds of other apes, or so there's some evidence for that. But there's one huge difference between them as natural psychologists and us, and that is they never get to compare notes. They never get to argue. They never get to get into the space of reasons and justify their attributions of beliefs and desires to other apes. It's just not part of their world. So I'm going to leave out the whole theory of mind debate in animals. It's something that has interested me for years, but I'm going to leave that out. So now I'm ready for one of the punchlines, and that is, Here's this, I love this diagram of the tree of life. It's available on the web, by the way. Let's see if I can read this name. Eisenberg, yeah, Leonard Eisenberg. If you go to the web, you can get beautiful sweatshirts and T-shirts with this on it, posters. And it represents from the origin of life. Here's the bacteria, the archaea. Then we have all of these eukaryotes. Almost 4 billion years of life. Lots of these insects, mollusks, fish, spiders, worms, they make things. Over here, we make things. Beavers make dams, spiders make webs. Amoebas make wonderful little castles that they live in. There's reasons for all of these, but we're the only ones that are like Gaudi. We're the only ones that have reasons for the things that we make. We are the first intelligent designers in the tree of life. And our natural tendency to interpret all design as top-down, this is the old-fashioned way, the pre-Darwinian way, as representation-driven, is both anachronistic and anthropocentric. There we are, way out on that little recent fringe of the tree of life, and we take a feature that we and we alone have, and we then import it back onto all the rest of nature. Very myopic of us. In the beginning was the word. I seem to recall that phrase from somewhere. It's from the Bible, of course. John. And I think, no, so it's not true. Words are a very recent invention. One of the most recent products of blind, purposeless natural selection. But they are the beginning of intelligent design. Gaudi type of design. We, the reason representers, we can now look back and discover the reasons everywhere in the tree of life. It took Darwin to figure out that a mindless process discovered all those reasons. We, intelligent designers, are among the effects, not the causes, of all those purposes. Okay, that takes us to my fourth point, which will be swift because I've run out of time, run over time. The intentional stance. Back to my cartoon here in the word why. As I say, we're the reason representers. Robert Brandom is reticent about why we represent reasons. It's just something we do, he says. That's the philosopher Strawson says something similar. And I just say, no, this won't do. After Darwin, we can't just say, well, that's just human nature, and leave it at that. There has to be a reason why we do these things. My answer is that we have evolved, along with a lot of other animals, the intentional stance, which is the instinct, when you see something complicated, immediately to try to treat it as an agent, as what I call an intentional system. Attribute beliefs and desires to it and rationality. Why? Why is it a good idea to have this on a hair trigger? Whenever you see something move, you want to ask, what does it want? Because it might want you. And in which case you want to know what it thinks and which way it's going to run and so forth. It's an instinct that we share with a lot of mammals and birds and maybe even fish, and certainly cephalopods. But we're the species in which language renders the intentional stance visible. This my point about Humphrey. We're the natural psychologists that compare notes. Purposes, reasons, beliefs, desires become objects to consider, to investigate. We can talk about them, we can reason about them, we can think about them, we can evaluate them. Now, when science first got started, we were animists. We treated everything from the intentional stance. The river wanted to find its way to the sea, and everything in nature was treated as a sort of agent. And this, of course, also grew out of early sort of proto-science religions, where you have If there's a thunderstorm, you want to know why. Why are you doing that? And you treat that, you have a rain god or a thunder god. So initially, we treated all complicated, interesting things from the intentional stance. The lodestone had a soul. Today, now that we have modern science, we can retrospect that this was an overextension. And a great deal of modern science has been the laundering of misguided anthropomorphism and misguided intentional stance application from the sciences. Why? Because it was a good trick that was overused. But now, and this led to the de-animization of the world, but now I think science has overshot in the opposite direction. I was mentioning this at the outset. Those who think thou shalt not speak teleology. Now, it's quite all right if you know what you're doing. You know, thou shalt not endow material things with minds. Hang on, don't we want to treat us as all having minds? We've got brains, we're going to be good materialists, but we want to use the intentional stance. There's an anecdote about this Sidney Morgenbesser once said to Skinner, who, remember, he was opposed to teleology, and he was opposed to the intentional stance. And Morgenbesser, classic line, said to Skinner, "Wait a minute. Are you telling me it's wrong to anthropomorphize people?" Which was basically Skinner's position. So back to Marx. Not only is a death blow dealt here for the first time to teleology in the natural sciences, but their rational meaning is empirically explained. I think, yes, the rational meaning of teleology is empirically explained by Darwin. Marx had it right. But that's not the death blow to teleology. It's the safety net that makes it safe for us to talk about the reasons that there are in nature. If you understand intentional stance talk in the evolutionist way, then you can see the woods for the trees. I say you can't do biology without assuming function. And you can't assume function without seeing reasons everywhere. It's okay. Some of my philosophical friends and opponents are not happy with this. They see my defense of reason in biology as Darwinian paranoia. Cute phrase. Alex Rosenberg calls it conspiracy theory. I call it an indispensable good trick. So, that's it. Two species of why questions, what for and how come. I explained Darwin's contribution is to show how we can unite the two, starting with how come and getting to why, to what for. We are the only reason representers, and the intentional stance is useful not just in the manifest image of everyday talk about agents like us, but in the scientific image as well. We can make sense of all the design in the biosphere. Reasons are real patterns in the world. I have this little pin I often wear, and it says, and of course it's got feet. And one day I was wearing this at an evolution meeting, and the physicist Murray Gell-Mann came up to me and he said, "Oh, I like your pin, Dan. You know that the Christian fish is really honoring the first acronym, and this is widely understood. Ichthus, the Greek word for fish, stands for Jesus Christos Theon Ios Soter, Jesus Christ, God's Son and Savior." So I said, "Thank you, Murray. I'd heard something about that before. Yeah, isn't that neat?" And he said, "Yeah, but I want to know, what does DARWIN stand for?" Well, Murray's a real polymath, and I couldn't do it in Greek. He could do it in Sanskrit and 3 other languages. But I did have a little leftover high school Latin. So I said, "Let me think about it." And I came back and after about a cup of coffee and a half an hour, and I said, "Oh, I think I can tell you what DARWIN stands for." Of course, there's no W in Latin, but there's U, so there's W. So D-A-R-W-I-N. Do we have any classicists here? You can keep me honest? Okay, so what does it stand for? Delere, remember Carthago delenda est, destroy or delete? Auctorem rerum, the author of things. Ut universum, infinitum noscas. Destroy the author of things in order to understand the infinite universe. Thank you.
Well, thank you very much. I know we've run a little bit over time, and for those of you who have to go, I understand that. But I think it's a fantastic opportunity to ask Dan a couple of questions, and I'll limit it to 2 questions. Does anyone have a question they'd like to ask?
It strikes me that there's another way of interpreting in the beginning was the word, rather than interpreting it as a literal linguistic quality, but if we interpret the word as an algorithm. What do you think about that inversion of the...
How nice. Algorithm would be almost better if it was logarithm, because then we would have logos. But, but it's close. And that's, I hadn't thought of that. It's a nice idea. Let me just try to articulate back to you the idea, because I want to make it as clear as I can. What I'm saying is that in the beginning, we had blind, mechanical, purposeless processes, but those processes, some of them, had, as a matter of brute, unthinking fact, they had the power, they had the competence to increase the complexity of things in the world in certain directions, and eventually this took off and gave us the capacity to reproduce, and then we're off to the races with ever more creative algorithms making ever more wonderful functional parts, and arms races and all the rest of that. The word, yes. Well, that would be a very nice ecumenical reinterpretation, yes.
Thank you. I can tell there'd be many, many more questions, but I'm going to close the session now. I'm just wondering whether anyone else has the same how come question that's in my mind. How come I'm so lucky to have been here tonight to hear such a stimulating and engaging talk. So would you please join me in thanking Professor Dennett.